Well, good morning. It's 9:31 on Wednesday morning, the 15th of March, 2017, the Ides of March, the day, wasn't it, that Julius Caesar was assassinated a few years ago. But it's supposed to be Calculus 1, Math 125, and unfortunately I'm the only one in the room, so I will get started. I wish y'all were here. Hopefully some of you will be coming in. Let's get the slideshow set up from the current slide, and we'll go from there. Now, my mark in my book indicated we finished 3.6, but didn't get to do the preliminary questions. Now, mostly I find these are useful for you, not for me, but since you asked to do them, we'll do them, okay? And the first preliminary questions is on page 158, chapter 3, 3.6 exercise of preliminary questions. Determine the sign, either positive or negative, that yields the correct formula for the following. Okay? And here's the first one. This is the A one on number 1. Let me get my pen activated with a darker color. And it's d by dx, okay, can't write very well, of sine x plus cosine x is equal to, and the options are plus or minus sine x plus or minus cosine x. Okay? Now, each of those trig functions should only have one sign in front of it, either positive or negative, but not both. You tell me which one it is. Well, derivative of sine is positive cosine. So for the cosine, that should be the plus, not the minus, but the derivative of cosine is negative sine, so that should be the minus, not the plus. So that's what the answer should be for A. Okay? Now, it's the only thing that makes sense to me about this problem. Let me make sure that is indeed what they wanted us to do. 3.5 preliminary question. First derivative, oh no, 3.6. Minus sine plus cosine. Got it. Okay? B. D by dx. Let me get my pen back. Okay? And I hear myself say that. I never used to say that, d by dx, you know. But I tutored an Indian kid, friends of our family, in calculus, and he had studied in India. He was taking his comprehensive test for his master's, I guess it was. No, maybe undergraduate degree. And he needed tutoring in math, so we were doing some, and I found out this is at least him. I don't know if that's how all Indians say it, but that's how they do. But it sort of has a nice little ring to it, so I've found myself saying it, d by d. That's what I mean by that. D, okay. D by dx of secant x. Okay? It says plus or minus secant x tangent x. Okay? Which you were here to answer, which you think it is. Hopefully you know. And if you don't, just look a little above you at the summary and it shows you this one is definitely plus. Now, I guess we'll do the third one and then I'll come back and do the C one. D by dx of cotangent x. D by dx of cotangent x. Is that plus or minus cosecant x? Okay. I'm sorry. Cosecant squared x. Okay. Whoa! This thing irritates me. My screen will hold pretty well and then all of a sudden give way on me. Okay. Which is that? Well, again, Lance just above you at the top of the page, and you'll see that that one is the minus. Whoa, it didn't do it. Well, all right. And I think I mentioned to you before, one way of remembering this, and I think it's as good as any, is if you got the main function, as in sine, secant, or tangent, those are positives. Derivative of sine, positive cosine, derivative of secant, positive secant tangent. If you're doing a cofunction, cosine, negative sine, cotangent, negative cosecant squared, cosecant, negative secant, cosecant, cotangent, okay? That's how I remember. I don't like many of those little shortcuts because I get them confused, but that one is easy to remember. Mostly because I know derivative of sine is cosine, derivative of cosine is negative sine. Once that one's done, I remember all the others follow the same pattern. Okay, now, just try to remember what follows it, the sign, you know. Okay, which of the following functions can be differentiated using the rules we have covered so far? Okay, this is just which, oh, I didn't check the answers. We'll go back and check them in a minute. Okay, number 2, okay, which of these can be differentiated using the rules we've covered so far? Y is equal to 3 cosine x cotangent x. Well, what's your reckon? That's simply a product. It's the product of trig functions. We know the product rule for any functions, and we know the differentiation of trig functions. So this one can be used. That's a yes. I don't know how they answer in the back. That's the A one. The B one. Y is equal to cosine of x squared. Here we, I'm sorry. I'm going to have to pause to go down the. All right, so sorry about that. I just had I don't know if it's change of weather or if I caught a little bug, but last night and today I've just been having a lot of drainage problems, and I almost got choked. So I feel better now, but hopefully it will continue. Okay, how about this one? B. Y is equal cosine of x squared. No, we haven't done enough to do that one. The next section, I believe, is the one on chain rule. Yep, there's a slide right there. Once we do the chain rule, yes, we'll be able to do that. That's a composite function. We don't have any rules yet until we get the chain rule for what to do with a composite function. Sums, differences, products, quotients, yes, you can do those. It's composite, we got to do the chain rule first. Okay, how about C? And I don't know why the slides are acting up. Y is equal to e to the x sine x. Okay, now that's definitely a product rule, and if my memory's right, we have done, yeah, power functions or exponential functions, haven't we? I'm teaching 4 different upper level math classes, and I know that most of them have done this prior to now. I'm trying to remember. Okay, product and quotient rules. Well, haven't we done exponential functions? I can't remember. It seems like we have. This is bugging me now. Did we do them in Chapter 2? I don't see them in Chapter 3. I don't recall. Have we done? I know I have, but I can't remember if we have in the class. 3.6. By the way, I'll check the other two. 1B is positive and 1C is negative. We got those right. 2A, yes, product rule and trig rules. And B, not yet discussed how to differentiate a composite function. And that function can be differentiated. Yeah, it's product rule. I just couldn't remember if we had done exponentials. I thought we had, but then I was afraid that was a different class. Okay, so yes. Now let's move on to number 3. Let's go on and clear the screen. So yeah, this one was a yes, that was a no. Okay. Okay, so let's clear the screen and do number 3. Compute d by dx of sine squared x plus cosine squared x without using the derivative forms for sine and cosine. D by dx of sine squared x plus cosine squared x without using derivative forms for sine or cosine. If you were to use that, that would be 2 times the sine of x times the derivative of, well, no, that's still a chain rule function. We haven't done that yet. But what we have done, and it's the only way to do this problem with what you've got so far, is, what is sine squared plus cosine squared? 1. Derivative of 1 is 0. Okay? That's all they wanted you to do with that one, I'm pretty sure. And yeah, 3 is 0. That's all they wanted. All right? And number 4. How is the addition formula used in deriving the formula the sine of x prime is equal to cosine x? How is the addition formula? Oh, I know what they mean. Okay. When we're deriving sine of x prime, that part of it had me confused there. That was equal to cosine, then I thought this is what they meant, but as soon as I saw it was equal to cosine, this is the same as sine prime x equal cosine x, or d by dx of sine x is equal to cosine x. All those mean the same, okay? Now, how to use the addition rule? At first I thought, I thought they meant the addition of derivatives, and you don't have an addition of derivatives. They're saying the addition formula, this one. Remember, your limit would be, as h approaches 0, of sine of x plus h minus sine of x over h. Well, the addition, that's what they mean, the addition formula. That sine x cosine h plus cosine x sine h. That's the formula they use. Or at least that's what I interpret the addition formula they're talking about. The difference quotient for that involves the expression sine x plus h. The addition formula of sine function is used to expand that expression. Exactly what I said. Okay. Now, I think I already made the homework assignment for this, but just in case you didn't catch it before, do either 1 or 3 or both, any of the odds 5 to 23, any of the odds 25 to 33, either 35 or 37 or both, either 39 or 41 or both, and then there was quite a few of the rest, any of the odds 43 through 51. Okay? some of those, like 47, says you need a graphic utility. I think you could probably do it without it, but in case you need it, you don't have to if you don't have it. 49 seems to be just a think through word type answer, but think through it, okay? Don't get too bogged down with those. But go with it. All right, now we've already hit, in fact, on this page, we can't do this or this based on our knowledge so far, because those are composite functions. You got a sine function, you got a squaring function, and they're not added, they're not subtracted, they're not multiplied, they're not divided, they are composites, okay? Now, actually, now that I think about it, we could have changed this, if we had wanted to, the d by dx of sine x plus cosine x, because that's what sine squared is and cosine squared is. And we could have done those using product rules, okay? I'm so glad we didn't. I'm so glad we did it the other way. That would have been doable, not that hard, just a little on the tedious side, okay? So, but if you think about doing it, that would be sine x cosine x plus cosine x sine x, that's 2 sine x cosine x, plus cosine x times negative sine x, plus another cosine x times a negative cosine x, negative sine x, and that would have been negative 2 sine x cosine x, and positive 2 sine x cosine x plus 2 cosine x sine x is 0, which is what we got before. It's just a lot longer and more involved way and more fraught with places to make errors. But what we're going to do now is come up with another way, and this is the chain rule is used to differentiate composite functions that are not quite so easy to change to like product rule functions like that one was. For instance, y is equal to cosine of x cubed. We had one similar to this in the preliminary questions. I think it was x squared, and we just no little trick to this one. You need another rule, okay? Another one would be this one. Y is equal to the square root of x fourth plus 1. Square root of x to the fourth plus 1. Okay, both of those are composite functions. One is the composite of the cosine of the cubic function. Okay, the alpha g of x would be alpha be your cosine function, g would be your x cubed, and you're doing alpha of g of x, which is a composite function, not a multiplication. Okay, and the bottom one, you're doing the square root of a quartic function, you know, your function raised to the fourth power. You might even say that's a three-way composite, but really x fourth plus 1 should just be treated as a single function. Okay? Now, recall that a composite function is obtained by plugging one function into another. For instance, the composite of f and g, denoted as f circle g, this, okay, is simply this, f of g of x. Instead of your x, you put in g of x, okay? Now, for convenience, we call the f the outside function, g the inside function. Often we write composite function f of u, where u is g of x. And if you find that helpful, you can. So this cosine of x cubed is the functions y is equal to cosine u, where u is equal to x cubed. Okay? And let me clear off everything else out of the way here. most everything else out of the way. I'm going to leave that function there because that's the one we're going to do next. Okay. So here's the chain rule. I'll blow this one up for you. And probably even leave part of that one in there. Boom. Okay, there it is. If f and g are both differentiable functions, that's a requirement, then the composite function f composed with g of x, or f of g of x, is also differentiable, and here's what the derivative is. The derivative of a composite function is the derivative of the outer function, the f function, evaluated at g of x, then multiply that by the derivative of the inner function, g of x. Okay? Now, that's how I usually approach it too. And I don't know why, but I've run into a lot of students who like to take the derivative of g first and then take the derivative of f of g, not of g prime, but of g, and that works fine too. Just, I guess I like to start with the outer and work my way in. They sort of seem to like to start with the inner and work the way out. The thing for me is that just knowing myself, once I had taken g prime, then when I took the f prime, I might be tempted to put the g prime in there as the argument of the f prime. It's not. It's the g that's the argument of the f prime. So this is a way I avoided errors, but go with it. Okay. So that's your rule. They are not going to prove it right now. A proof of the chain rule is given at the end of this section. Yay, I can't wait. Okay, looking forward to that. All right, but let's go on. And it seems like if they're going to give it, they ought to give it at the beginning so you know what you're doing. But I'm not going to argue with them. Okay, I can't get the... Okay, there. Let's do calculate the derivative of cosine of x cubed. Well, the y prime would then be cosine primed of x cubed times d by dx of x cubed. Okay, I can't write worth of 2, but okay. That's what you do. The derivative of the outer times the inner, evaluated at the inner, times the derivative of the inner. Okay? Well, what's the derivative of cosine? Derivative of cosine is minus sine of x cubed, of the inner function, then multiply that by the derivative of the inner function, which would be 3x squared. Okay? So cleaning that up a little bit, and this may be why people like to do the derivative of the inner first, I don't know. I would write that as minus 3x squared sine of x cubed. Okay? And there's no real reason to write it that way, except I like to get the signs and the numbers out front, so that's why the minus 3 got out there. Minus was already there, but I brought the 3 over. The reason I like to put the x squared out front too, if you looked at that, glanced at it too quickly, you might think that's the negative sign of the product function, which isn't what it is. It's negative. It's the product of the 3x squared and the negative sign function. So that's why I like to put it in front, so you don't think that's part of the argument of the sign. Okay? It's just my little choice. Let's see what the book did. They did it that same way. Negative 3x squared sine of x cubed. Okay? The next one, I wish I hadn't erased it too, because I would have it, but I'll erase them all now and go back and rewrite if it'll come up. There it goes. Oh man, I can't breathe again. Here's your y is equal to the square root of x to the fourth plus 1. We've seen that one before as an example of a composite function. Now let's take the derivative of that composite function. So first thing I would do is write it this way. X to the fourth plus 1 raised to the 1/2 power. I don't like taking derivatives of a radical. I'd rather take derivatives of the exponent because I know those rules a lot better. I mean, I can do the other, but it's much easier to do it with the exponent rules. So y prime would then be 1/2 the argument x to the fourth plus 1 to the minus 1/2, because it's the exponent minus 1, then multiply that by derivative of the internal, which is 4x cubed. Okay. Oh man, I can hardly breathe. Again, I like to get the coefficients up front. The 2 will go in the 4 twice, so that's going to be a 2x cubed in the numerator, and the denominator a square root of x to the fourth plus 1. Okay? Now, some people might not like writing it like that. You can leave it in exponential form if you don't want to go back to radicals. But notice that the 4, the x, and the cubed are all, the x cubed are in the numerator part. The 2 was in the denominator, but also the x plus 4 to the minus 1/2. The minus sign puts it in the numerator, but the 1/2 power. So, that's how. The other thing is this room feels like to me is a little on the cool side. I know it's so cold outside. Let me just check the thermostat just briefly. Sorry about that delay too, but the temperature has come up a little bit, but I'm right under the vent, and I think the air is not quite as warm coming out as it normally is, just because it's so cold outside and these windows leak and that kind of stuff. So, but I'm far enough from them, I shouldn't be feeling that. But anyway, example 2, that's what we've got. I can't believe that in the text they left the 4 and the 2 in there without reducing them, but they did. I've got 2x cubed over the square root of x to the fourth plus 1. Okay? The 2 should go into the 4 as they have in the book. Okay, let's move on to example 3. I think I'll clear that as well and do example 3. Calculate dy dx for y is equal to tangent of x over x plus 1. All right. Oh boy. This is definitely a composite function. Your dy dx. Sorry, dy dx. They just changed. They changed notation on you, and then I changed it completely. So the eraser's not working. Okay. Dy dx. Doesn't sound like what the problem is. Goodness gracious, it's such a pain in the neck. This is, well, take the derivative of the outer function. What is the derivative of tangent? Derivative of tangent is secant squared. So that's secant squared of x over x plus 1. Okay? Times derivative of your inner function. This inner function is a quotient. So now we've got to use the quotient rule. And if y'all were here, I can almost hear you saying low D high minus high D low over low low, or something like that. So let's do that. The low is x plus 1, that's your denominator, times the derivative of the numerator, low D high. Derivative of x is just 1. Okay? Sorry, I'm having trouble breathing. Seems like I'm clogging up worse and worse. I took a break between classes to get something to drink, thinking that would help it, but frankly, it doesn't seem to have helped at all. So there's our low D high. Derivative of x with respect to x is 1. Minus high D low, which is x times derivative of x plus 1, that's 1, over x plus 1 squared, low low. Okay? Now, looking at that numerator, that's x plus 1 minus x. The x's go out, and that leaves you just 1 over x plus 1 squared. Okay? So, that's your differentiation. I would just, again, to make it a little clearer, I would put the 1 over x plus 1 squared times the secant squared of x over x plus 1. Okay, there's your derivative of that composite function. The sort of additional pain on this one was that it was a quotient, which was the inner function, so you had to use the quotient rule there. Let's see what they got. Secant squared, they put it over. Secant squared of x over x plus 1, x plus 1 over x plus 1 squared. Same thing we got. I just wrote the 1 over x plus 1 out front of the secant squared. Same answer. Okay. I'm sorry. I'm going to have to go get something else, clear my head one more time. I hate this. I don't know why this has started. Again, I'm feeling really chilled, which isn't so much the temperature in the room. I hope I'm not coming down with something. But anyway, I'm going to pause again and go get something else to drink. Picking up from where we were before, we're on page 160. In fact, just finished example 3, near the bottom of 160, and just about to start on example 4. Before I do, are there any questions that you had before I get started again? Okay, I couldn't hear all that. Chain rule, okay, that's what we're doing now. Okay, so you want me to continue, or you have some specific problems, questions? Okay. All right, so this is example 4, which is a chain rule. So I'm going to, because this one might be a little more involved, I'm going to clear the screen. The daily natural gas usage, we were just talking sort of about that, in a household follows a pattern given by, and here is the function, g of t, I guess capital G is gas usage, okay, is equal to 300 times 1 plus cosine, okay, and look at the argument of cosine, 2 pi t over 365. 2 pi t over 365. Okay. And that's cubic feet per day. For some reason my pen is very slow. Okay. where t equal 1 corresponds to day 1, meaning January 1st, and assuming that it's not leap year, find the rate of change of usage, the rate of the change of usage on March 1st, June 1st, September 1st, and December 1st. Okay? Now, when you read what they're asking for here, assuming it's not leap year, blah, okay, find the rate of change of usage. This is the usage. The G of t is the usage. The rate of change of the usage would be dg dt. Rate of change, time rate of change would be dg dt. So that's what they're asking for. dg dt. Okay? Well, I think it might make it a little easier to look at and calculate if we multiply the 300 through. You really don't need to, but to me that makes it a little easier. This would be 300 plus 300 times the cosine of 2 pi t over 365. Okay? To me, those parentheses just may be a little confusing. I'm sorry. That's just G of t. Okay. That's G of t. Now we want to do dg of t. dg dt. Okay. Because I thought it would be easier to take the derivative of this function than the other one. Well, what's the derivative of the 300? 0, because that's just a constant. Derivative of 300 cosine would just be 300 times, what's the derivative of cosine? Negative sign. Okay? Of the inner function, I'm going to put it in parentheses, 2 pi t over 365. But then you do the chain rule. See, what we did was the derivative of the outer function, which was the cosine, negative sign, at the same argument as this is our g of t in here. Now we do the derivative of the inner function. And what's the derivative of 2 pi t over 365? This right here, the t is a variable. This right here is the number, that's just the coefficient. And derivative of, say, at would just be a, right? So it's just that, times 2 pi over 365. Okay? Now again, I don't like following that, so I'm going to bring that up front and make that minus 300. Well, the 2 is going to make it 600 pi over 365. Combining this with that, minus 600 pi over 365. Now and that's all times the sine of 2 pi t over 365. Now, you could do a little bit of reduction, not a lot. You could divide 5 into this, and that would go 120 times, right? And 5 into this would be 73 times. And that's about all you can do to simplify. Not very much, but a little bit. But that might help a little. So it'll be minus 120 pi over 73 times the sine of 2 pi t over 365. So that's your derivative. That's the time rate of change of your gas usage of the year. Now that's assuming January 1st is day 1, t equal 1. So we want this for March. Well, if January 1st is 1, That means January 31st is 31. February 1st would be 32, and February is not leap year, 28th would then be 28 plus 31 would be 59. So March 1st would be 60. So for March 1st, you want to put a 60 in there. So I'm going to call this G prime of 60. That's March 1st. Okay? G prime of 60 would be minus 120 pi over 73 times the sine of 60 times 2, that would be 120 pi over 365, because I plugged in t equals 60 there. Okay? Now again, we can reduce a little bit. 5 will go into this 24 times, and 5 will go in that again 73 times. Okay. So that will be negative 120 pi over 73 times the sine of 24 pi over 73. Okay? Now, if you got a calculator, I would use a calculator on this. I don't have one up here. Okay? Yours will probably do it just as you go, right? So do the negation key, 120 times pi divided by 73, sine of, I open the parentheses for sine, 24 pi over 73. Close that parentheses. Press equal to see what you get. Negative 4.4349. Is that what you said? Negative 4.4349. Okay? Yeah. Now, what does that mean? Well, guess what? 1st of March, supposedly it's getting warmer. And on average it is. So sure, you would have a negative rate of change of gas usage, because the gas is used mostly for heating. Some for cooking, but mostly for heating. So therefore, your rate would be decreasing at that point. And that's exactly what we've got. Okay? In fact, the temperature should be changing pretty quickly around then, so it's a pretty large negative increase. All right, what we got to do next is June 1st. Okay? Well, we got up to 59 was the end of February. The end of March. March has 31 days. So that would be 90, right? End of March. 59 was the end of February. This is the end of March. The 31st of March would be 90 days. 30th of April would be 120 days. You added another 30 to that. 31 of May, because there's 31 in May, that was going to be day 151. Okay? And 1st of June would be 152. So we're going to plug in 152 to your G prime. Well, here is your G prime for any t. So what we're going to have now is negative 120 pi over 73 times the sine of 152 times 2, because you got a 2 here and 152 there. That would be 304 pi divided by 365. Okay? I don't know of anything that'll reduce there, so just plug it and see what you get. Negative 120 pi divided by 73 times the sine of, open parentheses, I think that's 304 pi divided by 365, close your parentheses, press equals, see what you get. Negative 2.589, or they did 885, yeah, that's fine, okay, yeah, they did a lot of digits. I don't think they have justification for them, but they did. All right, let's see if that makes sense. 1st of June is probably still getting warmer every day, and on average, not every day, but on average it usually is getting warmer because you haven't reached the peak temperature yet. And probably your gas usage is pretty low, but it's still declining, okay? So that looks reasonable for that. All right, now we've got to go to September 1st. Well, 31st of May was 151. The 30th of June would be 181. The 31st of July would be 212, I believe, isn't it? Yeah. I think that's right. 31st of August will then be another 31 days. That would be 243. And the 1st of September would be 244. Okay? So on this one, what I'm going to do is erase some of this that I'm not using because we've already done all those. Okay. It'll be a negative 120 pi over 73 times the sine of, it's 244. It's 2 pi times t. The t is 244. So it'll be 488 pi. 488 pi over 365. Now my guess right off the bat would be, I hope this is turned positive now because the 1st of September should be not as hot as it was and maybe cooling a little bit. Let's see what you get. Seven. Okay, that's what they got. 4.5017. All right, it's probably cooling a little bit, so your rate of usage is probably pretty low, and that's what makes this a pretty big number. You're not using a lot, but it is increasing relatively rapidly, okay, compared to what you were. All right, so the 31st of August had it at 243. I'm going to erase some more down here just so I have room to do. We've already gotten this answer, so let's get out of there. You know, an easier way to do this on the 1st of December, that'll be 30 days from the 31st of December. So let's do 365 minus 30. 365 minus 30, because it's 30 days before the end of the year. That would be 335. That's a lot easier than adding a month at a time. So we'll do negative 120 pi over 73 times the sine of 335 times 2 would be 670 pi, sorry, over 365. Now you can punch those numbers in. It'll work. Just because I'm used to reducing things, I would divide them each by 5 first, but that just takes too much time. So go on and do it as is. It'll give you should give you the right answer. And I would think it would still be a positive number because I would think it's still cooling. Okay? And what do you get? What's that? I can't hear you, sorry. Did you get a different answer? Huh? Okay. I hope I didn't screw something up in my trying to do a shortcut. I think that's right, though. Did you not get it? What did you get? Oh, you got a negative. 670. I think we're doing it right. It's 335 times 2. Hopefully it's 670 over 365. Still not getting it? Oh, there you go. Got it. 2.5500. Is that what you get? And then what's the next digit? 8, yeah. So when you round up to the 4th, you see the 8 would change the 9 to a 10. That would change that to a 0. That would change that to a 5. Yeah. So yeah, that rounds to 2.5, approximately 2.5500. Yeah. Same thing they got. Okay. What's that? Huh. Did they use the same date? I think I've already erased those. Okay. We use.
I understand, like they use the same thing. It's just they rounded on the last one. They didn't round on.
Oh, I see. Well, yeah, I didn't follow it with the calculator, so I don't know. So it says here, it's not surprising the derivative is negative in the spring as the usage drops as the temperature rises. The derivative is nearer zero in the summer, which we saw. That's a smaller one, okay, nearer to zero, as the weather remains warm and usage does not change. The usage increases substantially in the fall, still increasing in December. Okay, now, let's clear the screen. Most of that was calculator work. It wasn't. The chain rule you used at the very beginning and then didn't use again. But let's erase all that. It says it's instructive to write the chain rule in Leibniz notation. So if you have y is equal to some f of u, remember u is in some function of x, so that would be f of g of x, okay? Then if you're doing dy dx, that would be df dg, you might say, but g is u of x is equal, so that's df du times du dx, okay? Okay? And another way to express that, okay, time out. Christian Huygens. Pretty interesting character here. If you study certain areas, you're very familiar with his name, but outside of those areas, most people aren't. But Christian Huygens, one of the whoa, goodness gracious. My cord got wrapped around my chair and pulled my computer off. And wow, glad these things are fairly durable. First time that's ever happened. Such a pain in the neck. I really didn't like it. They put the plug here because I have a fairly short extension. So I'm cramped over here in the corner, and this handle here on the chair caught the wire, and that's what pulled it off. I probably should. So let's go back and see if we can zoom this in again. So Huygens, one of the greatest scientists of his age, was Leibniz's teacher in mathematics and physics. He admired Isaac Newton greatly, but did not accept Newton's theory of gravitation. He was wrong there. He referred to it as the improbable principle of attraction, because it did not explain how two masses separated by a distance could influence each other. It was improbable, but it worked. Okay, now, I don't know if he would buy Einstein's, which sort of superseded Newton's, but it's a lot more convoluted, so I don't know. So even though he was a brilliant scientist and must have been a pretty good teacher, interesting that though he admired Newton, he did not accept all of his theories, even some that were absolutely correct. I wonder which side he would have come down on their argument of who invented calculus first. Leibniz was a student, but he admired Newton, so that would be interesting to see. Anyway, they threw them in here. Potential paper topic if you haven't already done a paper. Okay. Well, evidently they don't have Evidently, they don't have this next little blurb. I thought they would, so I will put it in here. Then they changed this to say dy dx, and since y is f, they write this as dy du dx. And that's basically what the chain rule says. The derivative of the outer function, the f function, the y function, evaluated at g of x, which this is calling u, okay, then times the derivative of the g function, which this is calling u, with respect to x. Okay. Now, looking at it in this form, it kind of makes a whole lot of sense. If you were tempted to think, well, what if you cancel out the du? You can't. They're operators. You don't cancel out part of an operator. But it sure looks like it would make sense. That would yield dy dx. You just have an intermediate variable in there in between the y and the x. That's the u variable, the g function, okay? And you just put that in between. You first take the derivative with respect to the u, which is the g function, then take the derivative of that u, or the g function, with respect to x. And sure enough, that's how you march along. All right, I don't think they do example 5, so let's do it also. Imagine a sphere whose radius r increases at the rate of 3 centimeters per second. So I'm going to try to draw a sphere. I'm not too good at drawing spheres. Okay, there's a sphere. Sort of, kind of, a little bit. Okay? Now, its radius would be here. There's its radius. Its radius is increasing at a rate of 3 centimeters per second. This is r, but the r is increasing a little bit. And when it says whose sphere radius increases at a rate of 3 centimeters per second. Okay? Use what that's telling you. It's a change of radius, right? Radius is measured in centimeters, right? And it's changing at a rate of 3 centimeters per second. So basically what that represents is dr dt. That's equal to 3 centimeters per second. Use your units to help you see what the derivative is. Okay? The rate at which the radius is increasing is that. At what rate is the volume increasing? So in here you have the volume of that sphere. Do you happen to know what the volume of a sphere is? Yeah, you could. Let me see. Some books have them in some places. Front inside cover of your book. Okay, not the very first page, but the next page. Yeah, right there, bottom of the page. See the volume of a sphere? First page, very first. See that sphere at the bottom of the page? Right above there is its volume. You see it? Cubed, that's it. The volume is 4/3 pi r cubed. Okay? Now, what we want to do, it says, okay, at what rate is the volume of the sphere increasing when r is equal to 10 centimeters? So in other words, what we're looking for is dv dt. That's the rate at which the volume is increasing, right? Well, I don't see volume as a function of time at all. But I do see it as dv dr. I can see that times dr dt. Well, we got dr dt right up here, right? Can you get dv dt? If this is v, then dv, dVdr would be what? Take the derivative of this with respect to r. dVdr. What would that be? Oh, don't use a calculator, do it in your head. 4/3 times 3 would be 4 times pi times r squared. Exactly. So dVdr would be 4 pi r squared, which interestingly, really interestingly, if you happen to notice back there when you're looking at the volume of the sphere, you've just given the area of the sphere. Bizarre. dVdr is also the area of that sphere. Strange but true. Okay? So, now we know we can plug that in for dVdr. 4 pi r squared times dr dt, which is 3 centimeters per second. Okay? Well, we want to do this when r is equal to 10. So this will be 4 pi times, what's 10 squared? That would be 100 centimeters squared times 3 centimeters per second. Okay? Let's multiply our numbers together. 4 times 3 is 12 times 100 would be 1200 pi. And the units would be cubic centimeters per second. That's a good unit for change of volume or change of time. Volume measured in cubic centimeters, time measured in seconds. That's it. And if you really want to get a numerical value, multiply 1200 times pi, which will be something on the order of 3700, something like that. Right? $37.70, in fact, they say. And that would be cubic centimeters per second. So, if that radius is increasing at a rate of 3 centimeters per second every second, when it's at 10 centimeters to begin with, it's increasing 3 more centimeters from that, so a pretty big volume increase. 3,770 approximately cubic centimeters per second. Because that's going up pretty fast. And let's see. There we are. I couldn't find where we were on the page. Now, let's now discuss some important. Any questions on that? You said chain rule sort of gave you issues. Right. Okay. The reason we're looking for dVdt is because of what the problem was asking for. The problem said, at what rate is the volume V increasing? Blah, blah, blah. Okay? Well, the rate of increase is dV, that's the volume that's increasing. Rate usually means time, with respect to time. So that's what we're looking for. Now, remember on the last slide that was up here, I erased it to get to this one. I said, if there's an intermediate variable, and obviously there is, see, this has nothing to do with time, right? This is V and R. So there must be an intermediate variable of R. So dV dt would be dV dr times dr dt. Looks like the dr's cancel out, we've got the same thing, right? They don't, but that's a warm and fuzzy saying, yeah, this feels like it's the right direction. Well, you can do dV dr based on this, which is what we did here. They already gave us dr dt when they said the radius is changing at 3 centimeters per second. That's a change of radius per change of time. Centimeters per second, radius per time. So we just plug that back in here. This is another way of expressing the change rule. Remember that what they said, if this g was some variable they called u, okay, then this would be derivative of f with respect to u times derivative of u with respect to x. That's what we did here. Derivative of v with respect to r times the derivative of r with respect to t. That's what the chain rule does. Okay? Does that make any sense? Okay, a little bit. Yeah. Right. The key to this one is identifying what that means. Time rate of change of your radius, the rate of change of the radius of time is dr dt. So then when we came down here and it's asking for dv dt, but your volume formula doesn't have any t's in it, then break that into dv dr, which you can calculate, and then you're already given dr dt, so that product is going to give you your answer for the chain. Okay. That was example 5. So I think we're ready for theorem 2. There's Huygens again. Here's theorem 2. And I forgot to bring my watch up. Actually, I left it at the lake this weekend, so I don't have it. I meant to bring my phone up so I could see the time. I left it in my coat pocket. Today's just not meant to be a good day. But my head's clearer now anyway. Okay. Here's the second. The general power and exponential rules. Wait. Where did this come from? Well, this is building on the chain rule. If g of x is differentiable, which sure needed to be if we're going to take derivatives of it, then dx, d by dx of g of x raised to a power, that's going to be a chain rule problem. Now, I don't like this notation because on one glance it looks like this is g of x to the nth power. That's not what it is. It's g of x to the nth power. So I would have put this g of x in brackets there, so I made sure we knew what we're talking about. Of course, I can't write it in bracket until I reduce it, so here it goes reduced again. So if you're going to write it that way, I would put that in parentheses with the n out here. It's the nth power of g. Now the other way you could have written this was this. D by dx of g to the n of x. Okay? I really don't like that either, because usually when we write an n over a function, or you talk about squaring the function and taking that derivative of the function. Taking a derivative, you should put it in parentheses. So you got to make sure you understand what it's talking about. This is raising it to a power. Okay? And how do you raise it to a power? Well, the inner function is your g of x, the outer function is your power function. So you do the outer first, n times g of x to the n minus 1, then times g prime of x. Chain rule. Okay? Now this is for any number n. And I want to say any positive number n. Okay? If n were equal to 0, no, it still works for that. For any letter n. Now, what if rather than a power function, you had an exponential function? Okay, here your outer function is your e, your inner function is your g. Okay, so then this would be derivative of e to the x would be e to the x, evaluated at g of x, and then the outer function, the inner function, g of x, you take the derivative of that, g prime of x. So this one they wrote the G prime in front. Here they wrote it at the end. It doesn't matter where you write it. I like it in front better generally, okay? But it really doesn't matter. All right. So that's the rules. I'll blow that up again because I had to reduce it to explain what was being raised to a power. It wasn't the x being raised to a power. It was the function g being raised to a power. Okay. All right. Now, let's do example 6. And I'm pretty sure example 6 is not on your slide set either. And there's, interestingly, the old edition had another theorem. This edition doesn't. And I'm kind of glad because that other one was a bit bizarre, okay? And you really didn't need it. So let's do example 6. Let me just see how far it goes. That figure's not in here either. Okay. All right. Let's do it here. Okay. Let's do example 6. Find the derivative of, the a part of example 6 is y is equal to x squared plus 7x plus 2 to the negative 1/3 power. And remember when they said n could be any number? That didn't mean any whole number either. Any number. Okay? So we're perfectly fine. So what would you do first? Okay, you start with, this is a power function. Your outer function is a power function, so do it first. And that'll be a negative 1/3 of this function, x squared plus 7x plus 2. And then that's raised to the negative 4/3 power. Because you subtract 1 from negative 1/3. Well, 1 is 3/3. So you got a negative 1/3 minus a 3/3. That would be negative 4/3. Okay. Done? No. Okay, we still got the chain rule part. What goes next? Of the inside, which is 2x plus 7. Done. Now that might not be the form you want to leave it in. It's okay. It's a perfectly legitimate form, but I'm going to write it this way. Well, I'm going to bring that up front with the negative 1/3, so that'll be negative 1/3 2x plus 7. And why not leave it in this form? X squared plus 7x plus 2 to the 4/3. Okay, negative 4/3. I know, I don't know why I left that out. But I couldn't get my 4/3 to write properly. Okay, I like that a little bit better. The only reason I left it in that form, that's how they gave us the problem originally. Another way you could have written this is in the numerator you have, I'm going to put the minus out front, 2x plus 7. And in the denominator, you have your 3, and you have your x squared plus 7x plus 2. And since you moved it downstairs, that will be to the 4/3 power. Okay? If it's upstairs, it's the minus 4/3 power. Downstairs, it's the 4/3 power. And then you could have written that as the cube root of that thing in parentheses. And that raised to the 4th power, but I don't see any reason to do any further. Let's just see how they wrote their answer. I Can't find it. They didn't do it. No, there it is. They left it in that first form that we had it. They left it in this form right here. Negative 1/3 x squared plus 7x plus 2 to the negative 4/3 power times 2x plus 7. Okay? Can we do the B part? Let's try it. Y is equal to e to the cosine t. What is your y prime? dy dt. E to the cosine t, because that stays the same, but then you multiply it by the chain rule part, and that would be the derivative of cosine t, which would be negative sine t. Okay? Now, if I were writing this, I'd put the sign in front, the SIGN sign in front, the sine t in front, and make that minus sine t e to the cosine t. You don't have to, but to me, especially if I'm writing sloppy, which of course it would never be, if I wrote this a little too high, you might think that's part of the code of the exponent. It's not. So putting out front indicates no, that's not part of the exponential function at all. It's in front, and there we go. Okay, let's see how they wrote it. They wrote minus sine t. They put it in parentheses. That's all. E to the cosine t. Very good. All right. I know we're going to need more room on the next one. Okay. Goodness, my head just clogged again. What's the time anyway? I don't have my watch. 11:04. Okay, so we got another, what, 6 minutes is all? Yeah. Woo! Okay. See if we can get example 7 done. Calculate this. D by dx of the square root of 1 plus the square root of x squared plus 1. Ew, my word. Okay. Now, the first thing I would do is not write this in radical notation, but write it in exponential notation. Now, that gets a little messy, but it's still better than radical notation. So I'm going to rewrite this as d by dx. I'm not taking the derivative yet. I'm just rewriting. That would be, I think I'll put a big bracket out here, 1 plus parentheses x squared plus 1. That's to the 1/2 power. And the 1 plus all that is to the 1/2 power. Okay? So, this thing that's in here, okay, this is this part right here. X squared plus 1 to the 1/2 power. 1 plus that is what you're raising also to the 1/2 power. Okay. Now, frankly, for me, this is easy to see inner and outer. Okay? So let's start with this 1/2 times the entire function there, right? Now we're taking the derivative. So that would be 1/2, this entire function here, 1 plus x squared plus 1 to the 1/2 power, and that goes to the negative 1/2 power. That's step 1. Okay? That's your outer function step. Okay? That's this part. This does this go. Now, the next step is to do the derivative of the inside. Okay? Well, the derivative of 1 is 0. I'll do that. Okay? But the derivative of this, the inner part here, and this is times a 1/2. Oh, EJ. Yeah, you're not, and this is your own trick. Thank you. All right, no problem. Okay. That would be, derivative of this would be another 1/2. This is times x squared plus 1, and that's to the negative 1/2, right? You did the 1/2 times this thing to the minus 1/2. Now you're doing the derivative of the inside. Derivative of 1 is 0. The derivative of this is 1/2 times this. And that then is to the negative 1/2. But you still got another inside here. The derivative of that one is 2x. You got it. Okay. So that's times 2x. Now, to get things where they belong. All right. In this very first part, everything's in the denominator. The 2's in the denominator, and this is in the denominator. So I'm going to write this as, starting my denominator, a 2 here, and then this is a square root, because it's to the minus 1/2, it's downstairs, 1 plus the square root of x squared plus 1. Okay. Huh? Why did I do that? Okay. Here's my dumb little thing. Since they gave me the problem of radicals, I worked it out using exponents, but then I got this feeling they want it back in radicals again. So that part there, the 2's in the denominator, and this part, because it's a minus 1/2, is in the denominator, and that's this thing right here. Okay? Now, there's another 2 in the denominator. But the good news about this one, I'm going to cancel those 2's out. Okay? Divide them away. Okay? Because one's in the denominator, one's not. Okay? But we still got, in this denominator, another x squared plus 1, the square root of x squared plus 1. That's in the denominator. But then your x is up here. So that's what it really turns out to be. Now, whether they do this, I don't know. Okay, let's see how they write their answer. No, they left it in. Good for them. Okay. They left it exactly like we did. 1/2, they brought the x out front. 1/2 x, so they brought 1/2 x. They brought this x over to here. And then they did 1 plus x squared plus 1 to the 1/2. That's to the minus 1/2. And the 2 canceled out already, times x squared plus 1 to the minus 1/2. Okay. Let's see if that's what they did. 1/2 x. Well, then they brought the x squared plus 2 to the minus 1/2 out front. And then that's times 1 plus x squared plus 1 to the 1/2. X squared plus 1 to the 1/2, but the whole thing to the negative 1/2. Yeah. I like it. They left it like this. I would have guessed they wanted it back in radicals, but they didn't. Okay. Did that run us out of time, or do we still have a little bit more? What is it?
It's
11:11. We went past it. Sorry. No extra charge, though. Okay. All right. So we'll begin next time on example 8. Okay? And homework exercises here. We almost finished 3-7. Do either 1 or 3 or both. Do 5. Then do either 7 or 9 or both. Then do any of the odds 11 through 21. Do either 23 or 25 or both. do 27. I think you can do, let's see, oh, last thing we've got to do is just sort of a pain in the neck, but okay. Where did I leave off? Through 41? And then I think you can do any of the odds 43 through 71. There's a whole bunch of those. I think you can do either 73 or 75. And we'll leave the rest of them till next time. Well, maybe not. Then do any of the odds 77 through 85. Now, on looking at that, number 82, which is not one you have to do, but that is an example of the von Bertalanffy growth function. If you wanted to choose that Carl Ludwig, he's a biologist, not really a mathematician, but if you can relate how he used calculus in coming up with that, that might be a good paper topic. I've never heard of the guy before I read this problem. Okay. Let's see, that through 85. And then there's, you could do either 87 or 89 or both. And you could try doing any of the odds 91 to 97. Okay? So yeah, it basically is most of those, because the only thing we still have left to cover is trigonometric derivatives in degrees, which is just a pretty minor little thing. And in reality, when we do it, you'll see we already did it. Okay, in an earlier example. They just didn't tell you you were doing that. No, not quite, but it was similar to it. All right, good deal. We'll pick up and go from there.